Hey students, good to see you guys working so hard, getting a lot of questions here. Thought I'd make a video of this one. The actual question I got was a little bit deeper, if you will, or kind of off-centered from this question. But I thought I'd work out this question. But I start by just saying the student was asking, and so I want to make that clear that, sometimes you see this equation that says the voltage is some initial voltage times e to the minus t over tau. And other times you see this equation, which is V naught 1 minus e to the minus t tau, where tau is our time constant, our RC time constant. And the short answer to that question is this is what you use when you are discharging something, and this is when you are charging it up. So if we're talking about kind of actually building one of these, we'd probably do something like this. We'd probably take a power supply, so I'll take here a V naught. And then we would connect it through a resistor and a capacitor. And as the charges flow, the capacitor is building up. And so if you plotted the voltage as a function of time, it would look like this. And that is this equation right here. Then that is the equation I would use when something is being charged up. Now, when something is being discharged, and so, let's say I left this for a while and it charged up, then what I might do is I might come along and I might, disconnect the battery and then just connect the capacitor resistor system back to itself, and now it would begin to discharge. And so the voltage as a function of time would look like this. It would decay away. And in that situation, you would use this equation. And like I said, that's kind of the crutch of this question. And we're going to have to decide that along the way as we read this and decide, are we charging up a capacitor or are we discharging it? Now, as a side note, you can see that in the mathematics, if you remember from your pre-calculus, where you would work with functions. You would have things like f of x, and then you could do something like this. You could take that function and then add a constant to it. And that shifts things along the x-axis. You could also take a function and multiply it by something out in front, and that's really the difference between these two. Now, in your math class, you probably also did this. You shifted things on the x-axis or expanded them on the x-axis. And so, things like this shift it up and down. Things like this make it get bigger along the y-axis. Or if that's a negative number, shift it over. And I think you can see that. If you took this function, which is represented right here with this mathematics, and you put a negative in front of it, that would shift it over. And so this going from this function, which is this, and putting a negative in front of it would shift it over like that. And then if you wanted to move it up on the axis, you would add a constant. And so we're kind of doing both of these when we go from here to here. We put a negative multiplier in it, which shifts it over. It doesn't make it bigger or smaller because it's a -1, so it just shifts it upside down. And then the +1, that constant, shifts it up. So this green one, the negative sign shifts it over, and then the +1 shifts it up to here. And so that's what that looks like. And I guess that's not real important for this problem. This is kind of just a little math review, but this is what we're essentially doing, and we're using our pre-calculus mathematics to say, what's the difference between a discharge and a charge. Now, we could actually then shift it along the x-axis by multiplying by a different constant, or shift it to a different location, depending on that constant. This one here would be done maybe in this real problem in a defibrillator, because when you're charging it up, you're going through one resistor, which is in the machine, and then when you're discharging it, you're taking the little paddle and putting it on the patient, and so that capacitor is discharging through the patient. And so that would be a different resistance. And so my picture here kind of shows the same resistor on charging and discharging, and that's probably not the case. In fact, if you ever played with these, they do take a little while to build up their charge. And then once they build up the charge, then you put the paddles on the patient, and you're really trying to release that in a huge pop of energy to stimulate that heart, or I guess maybe to shock the heart, because it kind of stops everything, and then you kind of let nature go, okay, pick up right. So if it's kind of gotten in a like an AFib, and then it's in a terrible pattern, you just kind of want to shock it, and that kind of messes everything up. And then hopefully the brain comes back and says, okay, wait, let's start it again, and hopefully starts it in the right pattern and gets it out of that AFib situation. Anyways, but I digress, but hopefully in a helpful way for you guys in the life science here. But like I said, the main crutch of this question, somebody was asking about charging and discharging. So let's read this and decide whether we are discharging or charging here. And so it says a heart defibrillator being used on a patient has an RC time constant, and they give us the value of 10 milliseconds. So we're going to use this equation here. That's the 10 milliseconds. Due to the resistance of the patient and the capacitance in the defibrillator. Okay. So when it is discharging, the resistance is the patient themselves. So we're talking about a discharging situation. So we're going to focus on this equation. Whereas if this question was talking about the capacitor being charged in the machine before we take the paddles and zap the person, we would use this equation. Now, the good news is the time constant has the same formula. It's a different R. Because like I said, this would be the R in the machine charging it up, and then on discharge, this would be the R of the patient as it is discharging through the human tissue. And so that's our clue here. It says due to the resistance of the patient. They're talking about a discharge. They're talking about when you're zapping the patient. And so I'm going to be using this one. That's my clue. All right, so let me get this mess out of the way and actually then dive into the problem here. So part A, maybe I'll just put here, chapter 21, number 69. I have this time constant equals to RC. And so the question says here, if the defibrillator has an 8 microfarad capacitor. Now, that kind of helps to know the physical picture of what's going on in our defibrillator. It's going to be the same capacitor. So whether we're talking about charging up the capacitor and then using that capacitor to stimulate the heart, to zap them, it's the same capacitor. So whether charging or discharging, we're going to use the 8 microfarads. But when it says, what is the resistance of the path through the patient, that's our clue that we're going through the discharge process. We are taking this charged capacitor, we're putting it on the patient, and we're going to find the resistance of the patient during the discharge. So I want this formula and this formula. This is the discharging one, and then this is our time constant. And in this case, we can just simply rearrange it. R equals time constant divided by C. And I'll just change the order R. So I'll put time constant, which is 10 milliseconds. And over here, I'll put capacitance as, what would it say, 8. And it said micro, that's 10 to the minus 6, and it's farads. So I'll start with the numbers. That's the easy part, if you will. It is 10 microseconds divided by 8 microseconds. And so that makes 1,250. And as long as I'm here, let's work with these units, because these units are probably new to most of you, and it's good to kind of practice these a little bit and really go back to our chapter 1 on working with units. So I'm going to put seconds in the numerator and then go back to farads. If you remember, the definition of a capacitance is charge per volt. And so that means the unit farad is a coulomb per volt. Coulomb volt. We like to put in square brackets when we're dealing with units here. So I'm going to put coulombs here and, well, instead of putting it per volt, let me just flip it and put the volt up on top, okay? Now, what's nice about this is we, usually don't like to make compound fractions. But I think it would help with the unit is to write coulombs per second. And so take the second off the top and put it down there, because a coulomb, excuse me, per second is what we called an amp. And so now I have the unit volt over amp, and that was the definition of an ohm. And so sure enough, as it should come out, our unit for resistance is in ohms. So this part A should be 1,250 ohms. Okay. And then B says, if the initial voltage is 12,000 volts, so 12 kilovolts, how long does it take to decline down to 600 volts? And so notice it says decline. Notice it's a discharging through the patient. Again, more evidence of why we would want to use this as opposed to this. So the voltage as a function of time would be the initial times e to the minus t over tau. And so the initial is 12,000. All right, 12 kilovolts. And it's going to decay down to 600, and we are asked, what was it, how long does it take? So we're asked to solve for time and the decay constant through the patient. No point in going back and remultiplying. The resistance we found times the capacitance. We know that this is 10 microseconds. So maybe I'll just go 2 steps in my mathematics and take that 600 and divide it by 12,000, and we're looking at 0.05. And maybe it was good we were talking about our pre-calculus, because then to get this time and to solve for it, I got to get out of the exponent. And to do that, I have to apply a natural log to both sides. So this would be the natural log of 0.05. And the natural log here undoes the exponent, so this would be a negative t over the 10 microseconds. In fact, I'm going to just go minus 10 and leave it as 10 microseconds. That way my answer will be in microseconds. All right, but grabbing my calculator, this is the log of the last answer. And sure enough, it's a negative number. It looks like it rounds to a 3. So this is a negative 3 equals a negative t over 10 microseconds. The 2 negatives cancel off, bring the 10 over to there, and that becomes 30 microseconds for the time frame. All right. Hope that was helpful to somebody. Take care.